Welcome back, everybody. Today we're going to talk about exponential equations, and we have two objectives. Our first objective is to solve exponential equations with like bases, and then our second is to see about solving exponential equations with unlike bases. All right? But first we need to talk about what an exponential equation is. So if we have something in the form, let's say like y equals a to the x power, all right, where x is a variable, that would be an exponential equation, all right? So here's my first example. I have 25 to the x power equals 125. All right, now this falls under the exponential equations banner because my variable is in my exponent. All right, now basically what I want to look at is can I take each base, now in this case the base is 25, exponent is x, and over here it's 125. Can I take those two numbers and rewrite them with the same base? Well, 25 can be written as 5 squared raised to the x power, right? And 125 could be 5 to the third power, right? Well, these now are considered the same base because when I raise a power to a power, as I said in the last section, we can multiply. So it's 5 to the 2x equals 5 to the third. Now, do you guys remember that one-to-one property we talked about where we said if we have we're doing the same operation on both sides, that we could strip away the operation and just look at the numbers? Well, something very similar happens here. We have the same base, right, 5, and we're raising to, in this case, an exponent of 2x, in this case, an exponent of 3, but the numbers are equal. What that means is that 2x has to equal 3. All right, and if 2x has to equal 3 in order to keep the numbers equal, then x has to equal, let's write that a little bit better. X has to equal 3/2. All right, and again, it's called the one-to-one property, but it's really important that you understand that with the same base, the exponents have to be equal. So there's our first equation where we solved by making like bases. All right, let's try another one where we make some like bases. So I have, example is 9 to the x power equals 3 to the x plus 1 power. All right, now it's pretty apparent that I can make this 3 squared raised to the x power, and it equals 3 to the x plus 1. So that's 3 to the 2x equals 3 to the x plus 1. And then again, I can use my one-to-one property to say 2x equals x plus 1. Subtract x from both sides, and I get x equals 1. All right, so by far, the easiest way to solve an exponential equation is if you can put them into like bases. Now, unfortunately, that's not always the case. All right? So the second case we're going to look at is, what if we can't put them into like bases? What are we going to do then? Well, here's my example, and we'll talk as we go. So I have 5 to the 2x minus 3 equals 3 to the x plus 1. All right, now it's pretty apparent that I can't rewrite 5 to be in some base 3. I can't rewrite 3 to have a base of 5. So we have unlike bases here. So we have to get our exponents, we have to get our variables out of the exponent. So how are we going to do that? Well, we're going to do that by taking the natural log of both sides. And the reason we're going to take the natural log of both sides is because now we have a power property that says I can say 2x minus 3 times ln 5 equals x plus 1 times ln 3. All right, and the reason I use natural log a lot is not because there's any special thing in this case for natural log, but when you get to calculus, natural log has some very interesting properties that you can use. So I want you to get used to just the idea of just using the natural log as kind of your go-to log. All right, you can use log base 10, you can use log of any base when you're doing this, but natural log, like I said, when you get to calculus, if you're used to natural log, it's going to make that transition a lot easier with certain topics. All right, so now what I need to do is I need to distribute this ln 5. So I have 2, and I'm going to put the x over here so I don't get mixed up with my ln 5. All right, minus 3 ln 5 equals x ln 3 plus ln 3. All right, so again, all this does now is we have to just do a little bit more algebra. All right, so now what I want to do is I want to bring this to this side. I want to bring this to that side. So I have 2x ln 5 minus x ln 3, if I subtract it from both sides, equals 3 ln 5 plus ln 3. All right, so now I have a common factor of x, so I'm going to pull that out, and I have 2 ln 5 minus ln 3 equals 3 ln 5 plus ln 3. Now I'm going to divide both sides by what's in my parentheses. And I get x equals 3 ln 5 minus, or plus, excuse me, ln 3 over 2 ln 5 minus ln 3. And at this point, you just have to leave it. The only way to go further is if you had a calculator, and in my class, you don't have one. All right, so this would be your final answer. Let's try another one, see how it works. What about something like this? 5 times 2 to the x minus 3 equals 17. All right, so on the right side, I have 17, which is a prime number. And on the left side, I have a base of 2. Doesn't seem like I can make like bases of any sort. So I have to just start working from here. All right, so the first thing I'm going to do is I'm going to divide by 5 because I want to isolate my exponential expression. So I have 2 to the x minus 3 equals 17 over 5. And again, I'm still not looking to make like bases because it just can't happen. So I'm going to take the natural log of both sides. And let's see how this works. So I have, I'm going to use my power property to say x minus 3 times ln 2 equals ln 17 over 5. Now, there's a couple of different ways we can go with this, but I'm going to use my division, my quotient property, just because we just did it in the last section. But I can distribute the ln 2, so I get x ln 2 minus 3 ln 2 equals the ln of 17 minus the ln of 5. All right, so now I'm going to add 3 ln 2 to the other side. So I get x ln 2 equals 17, nope, ln 17, excuse me. And now I'm going to divide both sides by ln 2. So I have x equals ln 17 minus ln 5 over ln 2 plus 3, because if you divide everything by ln 2, those two would cancel. So it looks like this would be my answer in lowest terms. All right. So that was an interesting one. Had a little bit of an algebra twist right at the end. But let's take it to the next level and see how we do. I always like to take things to the next level if we can. So I have 9 to the x power minus 6 times 3 to the x power, plus 8 equals 0. Now here, what do I see? I have two exponential expressions. They're both on the same side, right? And one is the one base is the square of the other. So I'm going to do something slightly different. I'm going to use a substitution in order to make my life easier rather than try to figure everything out with exponential expressions in it. So I'm going to take the second one. I'm going to go u equals 3 to the x. And that means u squared equals 9 to the x. And that's really what I wanted, was I wanted to substitute for my exponential expressions. So this way, I can get rid of both of them. And I can say u squared minus 6u plus 8 equals 0. All right. Now I have the same equation, but I just have it where I'm solving for u right now. Okay. And solving for u, in this case, is going to be a whole lot easier than dealing with those exponential expressions the whole time. Because from here, I'm going to factor, and I'm going to say u minus 4 and u minus 2. Just checking, make sure that's right. Then u minus 4 equals 0, u equals 4. U minus 2 equals 0, u equals 2. Excuse me, hang on. U equals 2. There we go. All right, but we're not quite done yet. All right. What we wanted to know is what x equals, right? Because we said solve for x. Now, we chose to do a substitution in order to make our algebra a lot easier. But we can't finish on what u equals. We have to substitute back. So now I'm going to change color for contrast. U is 3 to the x. I'm going to say 3 to the x equals 4. And I'm going to take the ln of both sides. X ln 3 equals ln 4. And x equals the ln of 4 over the ln of 3. And that's about as far as we can go with that one. So in this side, we have 3 to the x equals 2. I'm going to take the ln of both sides. And I'm going to say x ln 3 equals the ln of 2. And x equals the ln of 2 divided by the ln of 3. So here are our two answers that we have. We can't go any further than this. This is all we can do. And they're both real numbers. But we can't get them without a calculator. And of course, in our class, we don't have one. So this is where we would have to stop. Now, we touch on inequalities just a little bit. So I do want to do an example or two with inequalities as well. Inequalities are going to be very similar to what we've been doing. So I have 5 to the 0.7 x plus 3 is less than 18. All right, so now we're going to observe all of the rules that we learned for inequalities, all of the rules that we learned for, algebra. where if I subtract 3 from both sides, I get 5 times 0.7 to the x power is less than 15. Now I'm going to divide both sides by 5. Remember, whatever you do to one side, you have to do to the other. So I get 0.7x is less than 3. Now from here, I look at it as an exponential equation, but it's one of those exponential equations where I can't have the same base. So I'm going to do what I've been doing for each one of them, which is take the ln of both sides. So then I use my power property to say x ln 0.7 is less than ln of 3. And then x is less than, if I divide by ln of 0.7, ln of 3 over the ln of 0.7. And I am done. All right. So I'm going to give you one more. And again, I got 3 times 0.5 to the x power plus 7 is greater than 19. All right, so the first, I want to strip away the things that are easiest to do. I want to isolate my exponential expression. So I'm going to subtract 7 from both sides, and I get 3 times 0.5 to the x power is greater than 12. And look at that. I can divide both sides by 3, and I get a nice number. So I have 0.5 to the x power is greater than 4. And now, because I cannot make them the same base, I'm going to say the ln of both sides. And then I'm going to use my power property. Again, x ln of 0.5 is greater than ln of 4, and x is greater than the ln of 4 over the ln of 0.5. All right, so I just knocked out a bunch of equations for you. Remember, this is just exponential equations. Next time we talk, we'll talk about logarithmic equations, which will have a few other wrinkles to them. But thanks for listening, and I'll see you guys next time.